Hello, welcome to this presentation. With over 30 years of experience in the telecom and wireless engineering domain, I have extensively reviewed standards documents, specifications, feasibility studies, technical reports, and peer-reviewed papers. Despite my deep passion for this field and continual desire to learn, I often found these documents less than engaging, particularly when they are lengthy and overly detailed. Recognizing the need for more digestible communication methods, I created this series to present 3GPP specifications in a simple, easy to understand PowerPoint format. My goal is to distill the essence of these complex documents into clear, concise presentations, allowing you to grasp the key points effortlessly through just listening. Simplicity, after all, is beauty. Through this approach, I aim to convey the core content of each standard succinctly and effectively. This particular specification is from 3GPP, titled 3GPP Technical Specification 22.104, and is part of the 5G system standards. It's crucial to understand that this is a stage 1 document, meaning it defines the service requirements from a user's perspective. These requirements will guide the development of stage 2 for architecture and stage 3 for protocol specifications. The version 19.1.0 indicates as part of release 19, which is focused on enhancing 5G capabilities for industrial and IoT applications. In the context of 3GPP specifications, release 19 builds upon the foundation laid by previous releases, particularly release 15, the first 5G release, and subsequent enhancements in release 16 to 18. It aims to address the evolving needs of vertical industries with a particular focus on ultra-reliable low latency communication, URLLC for short, massive machine type communication, MMTC, and enhanced mobile broadband, EMBB in short, in industrial settings. The specification process in 3GPP involves multiple stages. Stage 1 specifications like this one are technology agnostic and focus on the services and features from an end user perspective. They serve as the basis for stage 2 specifications, which define the functional architecture, and stage 3 specifications, which provide detailed protocol level implementations. This layered approach ensures that the developed standards meet user needs while allowing for technological flexibility in implementation. Let's begin. I also want to note that all the content and diagrams cited here are all from this 3GPP specification. This specification addresses the unique challenges of cyber-physical control applications. These applications often require ultra-reliable low-latency communication, a key feature of 5G. The document covers both service performance requirements and network performance requirements. Service performance requirements relate to what the user experiences, while network performance requirements define how the 5G system must perform to meet these service requirements. The specification also addresses Ethernet support, which is crucial for integrating 5G with existing industrial networks that often use industrial Ethernet protocols like Profinet or EtherCAT. These are acronyms. I hope I pronounced them correctly. Actually, I listed them here. If you look at the bottom of the slide, those are acronyms for industrial. Two of the examples of the industrial Ethernet protocols. Ultra-reliable low-latency communication in 5G is designed to support applications that require extremely low latency, as low as 1 millisecond, and high reliability up to 6 nines, 99.9999% success rate. This is achieved through various technological enhancements in 5G New Radio, NR in short, including flexible numerology, mini slots for shorter transmission times, and robust coding schemes. For industrial applications, ultra-reliable low-latency communication can enable real-time control of machinery, critical infrastructure monitoring, and autonomous systems. The Ethernet support mentioned in the specification is particularly important for industrial applications. Many existing industrial control systems use specialized industrial Ethernet protocols, each with its own timing and reliability requirements. The 5G system needs to support these protocols seamlessly, which involves not just carrying Ethernet frames, but also maintaining the strict timing and synchronization requirements of industrial protocols. This might involve techniques like time-sensitive networking, TSN for short, integration with 5G, where the 5G system acts as a TSN bridge, time-sensitive networking bridge, maintaining precise time synchronization across the network. Okay, let's get into cyber-physical systems a bit. What are the key concepts? In cyber-physical systems, the physical processes are controlled or monitored by computer-based algorithms. This integration is crucial in Industry 4.0 scenarios. The control applications often operate in closed-loop systems where sensors continuously feed data to controllers, which then adjust actuators. This cycle can occur hundreds or thousands of times per second in some applications. The vertical domains mentioned can include factories, as in discrete manufacturing, process industries, as in continuous manufacturing, energy grids, and healthcare. Each domain has its specific requirements, and we shall go through some of those later, which the 5G system must be flexible enough to accommodate. The concept of a cyber-physical system, CPS in short, represents a deep integration between computational and physical processes. In a CPS, cyber-physical system, I'll use CPS from now on, embedded computers and networks monitor and control physical processes, usually with feedback loops where physical processes affect computations and vice versa. This tight coupling between the cyber and physical aspects introduces new challenges in system design, particularly in terms of timing, reliability, and security. In the context of 5G, supporting cyber-physical systems involves more than just providing connectivity. It requires the network to be an active participant in the control loop. This might involve edge computing capabilities to process data close to the source, network slicing to provide dedicated resources for critical applications, and advanced quality of service (QoS) mechanisms to ensure that different types of traffic, sensor data, control commands, system updates, etc., are handled appropriately. The 5G system must also be able to adapt to the diverse requirements of different vertical domains, which might range from extremely low latency for factory automation to massive scalability for smart city applications. Let's take a look at 3 communication patterns: periodic deterministic communication, aperiodic deterministic communication, and non-deterministic communication. Periodic deterministic communication is crucial for applications like motion control, where precise, regular updates are needed. The period can range from sub-millisecond to seconds, depending on the application. Aperiodic deterministic communication is often used for event-driven control, such as emergency stops or alarms. When the timing is not regular, the latency requirements are still restricted. Non-deterministic communication might be used for less than critical tasks like data logging or software updates. The 5G system must be able to handle all these patterns simultaneously, often on the same network infrastructure. To support periodic deterministic communication, 5G systems employ techniques like semi-persistent scheduling, SPS for short, and grant-free uplink transmissions. SPS, semi-persistent scheduling, allows the network to allocate radio resources to a device at regular intervals without the need for explicit scheduling requests, reducing latency and signaling overhead. Grant-free uplink enables devices to transmit data without first requesting and receiving a grant from the base station, which is particularly useful for periodic low latency traffic. For aperiodic deterministic communication, 5G introduces features like configured grant, where resources are pre-configured for a UE, user equipment, to use when needed, and logical channel prioritization, which allows critical traffic to preempt lower priority transmissions. The system also employs sophisticated scheduling algorithms that can quickly allocate resources in response to sudden traffic demands. Non-deterministic communication in 5G benefits from features like network slicing, which can isolate different types of traffic, and quality of service (QoS) mechanisms that ensure appropriate handling of different traffic classes. The challenge lies in efficiently multiplexing these different types of traffic on the same physical infrastructure while meeting the diverse performance requirements of each. Next, let's take a look at the performance requirements overview. Communication service availability is typically measured over long periods, often expressed as a percentage. For example, 5 nines to 6 nines, like 99.999% availability. End-to-end latency includes not just network transmission time, but also processing time at both ends. For some applications, this needs to be in the sub-millisecond range. Reliability is often expressed as packet error rate or mean time between failures. The service bitrate requirements can vary widely, from a few kilobits per second for sensor data to gigabits, 2 gigabits per second for video streams. Survival time is a crucial concept in industrial applications. It's the time an application can continue to function safely without new data. UE speed, user equipment speed, and density requirements are particularly important for mobile robots and other moving machinery in factories. These performance requirements are interdependent and often involve trade-offs. For example, achieving very low latency might require compromises in terms of reliability or throughput. The 5G system employs various techniques to meet these requirements. For high availability, it uses features like dual connectivity, where a UE can be connected to multiple base stations simultaneously, and robust error correction coding. Low latency is achieved through techniques like TTI, short transmission time intervals. Transmission time intervals, the acronym is TTI. Edge computing and optimized network architectures that minimize the number of hops data needs to traverse. Reliability in 5G is enhanced through features like multi-connectivity, where data is sent over multiple paths to increase the likelihood of successful reception, and hybrid automatic repeat request (HARQ) mechanisms that quickly retransmit lost packets. The wide range of bit rate requirements is addressed through flexible numerology in 5G New Radio, which allows the system to adapt its radio parameters to different types of traffic. Survival time is an application-level concept, but the 5G system supports it by providing predictable performance and mechanisms for applications to detect and react to network issues. The UE speed and density requirements are particularly challenging in industrial environments. 5G addresses these through advanced beam management techniques for high-speed UEs and massive MIMO capabilities that can support a large number of simultaneously connected devices. The system also employs sophisticated resource scheduling algorithms that can efficiently allocate network resources among a large number of diverse devices. Okay, next we're looking at a diagram here. Performance requires overview. Again, all these diagrams are taken right out from the spec, so I'm not citing the source in each of these, but in the beginning of this PowerPoint, I stated that already. There are two key perspectives on dependable communication in 5G systems: the end-to-end perspective of communication services and the network perspective. Pardon me. The communication service may be implemented as a logical link between a user equipment, UE, and a network server, or between two UEs via logical components known as CSIF in short. Now, what's CSIF? CSIF stands for Communication Service Interface Function. As you can see on the diagram here, two CSIF, the Communication Service Interface Function, two of these functions, talking to each other within a 5G system functioning as communication services. To reduce latency, increase availability, or keep sensitive data within a non-public network, a local approach, for example network edge, may be preferred. This spec outlines requirements where periodicity and determinism are crucial for cyber-physical control applications across various vertical scenarios. These requirements highlight the need for the 5G system to be flexible enough to meet different KPIs, key performance indicators, specific to each use case. Communication service availability is critical for cyber-physical applications with deterministic traffic depending on latency, reliability, and the survival time of the application. Now, I'm going to talk about this key concept repeatedly at times during this whole presentation because that is a key concept. Communication service reliability is crucial for automation applications and is distinct from service availability requirements. The number of UEs involved in the communication indicates the UE density within a service area. Clock synchronization is essential for many vertical use cases, which provides criteria for managing time-sensitive communications in industrial environments. This specification has clauses outlining positioning requirements for high accuracy in industrial environments, emphasizing the importance of tracking mobile devices and assets for improving processes and increasing flexibility in factories of the future. And the future is here. 5G is being used everywhere these days, and implementations already have taken place. Details of the requirements are not in this presentation, so if you need to implement any of these concepts, you need to go back to the specification and look at those actual clauses and requirements in detail. In periodic deterministic communication, the transfer interval is a critical parameter. For motion control applications, this can be as low as 500 microseconds. The end-to-end latency must be less than this transfer interval to ensure that each cycle of the control loop completes before the next one starts. The communication service availability requirements are extremely high, often 6 nines, 99.9999% or higher. This translates to only seconds of allowable downtime per year. The system must also handle multiple simultaneous periodic flows with different periods, which requires sophisticated scheduling mechanisms in the 5G system. To achieve such low and consistent latency, 5G employs several key technologies. One is the use of mini slots in 5G NR, which allows for transmission duration as short as 2 OFDM symbols, about 140 microseconds in some configurations. This enables very frequent small data transmissions. Another key feature is ground-free uplink transmission, which I mentioned earlier already, where devices can transmit data within first requesting and receiving a scheduling ground from the base station. This can significantly reduce latency, especially for small periodic transmissions. The high availability requirements are met through a combination of robust physical layer design, including advanced error correction coding and MIMO techniques, and higher layer features like multi-connectivity. In multi-connectivity, a device maintains connections to multiple base stations or multiple carriers simultaneously, allowing for rapid failover if one connection experiences issues. Managing multiple periodic flows with different periods is a complex scheduling problem. 5G systems use sophisticated scheduling algorithms that can handle mixed periodicity traffic. This might involve techniques like earliest deadline first scheduling, EDF, earliest deadline first scheduling, or rate monotonic scheduling, adapted for the wireless environment. I'm not going into the details of how these scheduling mechanisms are implemented. You can look at actually a couple other specs that details it, or even you can Google it. There's information in the internet. The system must also employ advanced QoS mechanisms that can prioritize traffic based on its timing requirements and criticality. Aperiodic deterministic communication often has even straighter latency requirements than periodic communication, as it's often used for critical events. For example, an emergency stop signal might need to be delivered in less than 10 milliseconds. The service bitrate requirements can be high for applications like augmented reality, potentially reaching tens of megabits per second. The system must also be able to prioritize these aperiodic messages over regular traffic, which might involve preemption mechanisms in the 5G radio interface. The communication service availability requirements remain very high, as these messages are often safety critical. To support aperiodic traffic with very low latency, 5G systems employ several techniques. One is the use of configured grant transmissions, where resources are pre-configured for a device to use when needed, without without the delay of a scheduling request and grant procedure. Another is the use of logical channel prioritization, which allows high priority traffic to preempt lower priority transmissions. For high bandwidth aperiodic traffic like augmented reality data, 5G systems can dynamically allocate large blocks of spectrum using carrier aggregation techniques. This allows the system to quickly ramp up data rates when needed. The system also employs advanced congestion control mechanisms to ensure that sudden bursts of high priority traffic don't overwhelm the network. Ensuring high availability for aperiodic traffic is particularly challenging because the system can't rely on regular, predictable transmission patterns. 5G addresses this through features like ultra-reliable latency communication, which uses techniques like robust coding, frequency diversity, and multi-antenna transmission to achieve very high reliability even for sporadic transmissions. The system also employs sophisticated emission control and resource reservation mechanisms to ensure that resources are always available for critical aperiodic traffic, even in heavily loaded networks. While non-deterministic communication has less strict timing requirements, it still needs to meet certain standards. For software updates, integrity of the data is crucial. So the system might employ robust error correction and retransmission mechanisms. For video streaming, consistent bitrate is important to maintain quality. The UE speed requirements are particularly relevant for applications like remote-controlled vehicles in factories, where the network needs to maintain connectivity as the UE moves. The 5G system needs to balance the resources given to non-deterministic traffic with those reserved for deterministic traffic. Non-deterministic traffic in 5G benefits from the system's high capacity and flexibility. For large file transfers like software updates, 5G employs advanced error correction, coding schemes, and hybrid automatic repeat request (HARQ) mechanisms to ensure data integrity. These are complemented by higher layer protocols like TCP, which provide end-to-end reliability. For very large updates, 5G supports techniques like multicast broadcast, which can efficiently deliver the same data to multiple devices simultaneously. For video streaming applications, 5G uses features like quality of service (QoS) flow indicators to ensure that video traffic receives appropriate treatment in the network. This might involve techniques like guaranteed bitrate (GBR) bearers, which reserve network resources to maintain a consistent data rate. The system also supports advanced video coding standards and adaptive bitrate streaming techniques, which can adjust video quality based on network conditions. Supporting high UE mobility is a key feature of 5G, achieved through advanced beam management techniques and rapid handover procedures. In factory settings, this might involve dense networks of small cells to provide continuous coverage with techniques like coordinated multipoint (COMP) transmission to smoothly hand over connections between cells. The system also employs sophisticated channel estimation and prediction algorithms to maintain link quality even at high speeds. Balancing resources between deterministic and non-deterministic traffic is a complex task that 5G addresses through features like network slicing and dynamic resource allocation. Network slicing, which has been implemented in a lot of networks now, has been everywhere. This technology allows the creation of virtual networks with specific characteristics which can be used to isolate different types of traffic. Dynamic resource allocation algorithms continuously adjust the distribution of network resources based on current traffic demands and priority levels. Clock sync requirements. There's this protocol which a lot of you know. It's been around for quite some time. The IEEE 1588 version 2 precise time protocol can achieve sub-microsecond accuracy. The 5G system needs to transport these timing packets with minimal and constant delay to maintain this accuracy. The global time domain typically uses International Atomic Time, TAI for short, as a reference, while working clock domains might use a local reference. The synchronicity budget, usually less than or equal to 900 nanoseconds for global, less than or equal to 700 nanoseconds for working domains, includes all sources of timing error in the 5G system. Supporting 128 working clock domains requires the 5G system to efficiently manage timing information from multiple independent time bases simultaneously. To achieve such high levels of synchronization accuracy, 5G employs several advanced techniques. One is the use of precise timing protocol support in the RAN, in the radio access network, where base stations can act as transparent clocks or boundary clocks in the IEEE 1588 hierarchy. You can go and take a look at that protocol, the clock sync protocol. Look at version 2, 1588 v2. This allows timing information to be accurately propagated through the network. Another key feature is the use of synchronous Ethernet, synchronous Ethernet, in the backhaul network, which provides frequency synchronization at the physical layer. The 5G system also employs sophisticated algorithms for estimating and compensating for network delays. This might involve techniques like two-way time transfer, where timing packets are sent in both directions to cancel out asymmetric delays. The system also uses advanced filtering and smoothing algorithms to reduce the impact of jitter and wander in the network. Wander, like wandering around, packets wandering around. Supporting multiple independent time domains is a complex task that requires careful management of timing resources. The 5G system employs techniques like time domain isolation, where different slices or logical networks can have their own independent time bases. It also uses advanced scheduling algorithms that can handle mixed traffic with different timing requirements, ensuring that time-critical packets are given priority and transmitted with minimal delay. The tight synchronization requirements also have implications for the hardware design of 5G equipment. Base stations and core network elements need to have very stable and accurate internal clocks, often using techniques like GPS disciplining or ribbon atomic clocks. The system also needs to handle environmental factors that can affect timing accuracy, such as temperature variations and vibration, through techniques like adaptive clock recovery and dynamic calibration. Okay, positioning performance requirements. Positioning requirements are categorized into service levels. For example, service level 7 requires horizontal and vertical accuracy of less than 0.2 meters, 99% availability, and latency of less than 1 second. This level of accuracy often requires the integration of multiple positioning techniques such as GNSS, cellular positioning, and inertial sensors. The 5G system needs to support the transport of positioning data from these various sources and potentially assist in the positioning calculations. For some applications, relative positioning, which is position relative to other nearby devices, is more important than absolute positioning. To achieve such high levels of positioning accuracy, 5G employs a variety of advanced techniques. One key feature is the use of beamforming and massive MIMO technology, which allows for very precise angle of arrival measurements. This is complemented by time difference of arrival, TDOA in short, measurements, using the synchronization signals in 5G New Radio. For even higher accuracy, 5G supports carrier phase measurements similar to those used in RTK GPS, which can provide centimeter level accuracy under ideal conditions. The 5G system also supports hybrid positioning techniques that combine multiple sources of information. This might involve integrating GNSS measurements with cellular positioning data using techniques like assisted GNSS, ADAS-GNSS, where the network provides assistance data to improve GNSS performance. The system can also incorporate data from inertial measurement units, IMUs, and other sensors, using techniques like Kalman filtering to fuse the different data sources. For applications requiring relative positioning, 5G supports device-to-device D2D positioning techniques. These might involve direct ranging between devices using side-link communications, or cooperative positioning where devices share their location information. The system also supports techniques like simultaneous localization and mapping, SLAM, which can be particularly useful for applications like autonomous vehicles in industrial environments. The high availability requirements for positioning are met through a combination of network design and algorithmic approaches. This includes techniques like multi-cell positioning, where measurements from multiple base stations are combined to improve accuracy and reliability. The system also employs sophisticated error detection and mitigation algorithms to handle issues like multi-path propagation and non-line of sight conditions. The latency requirements for positioning are addressed through optimized network architectures and processing algorithms. Ethernet applications. So these are IEEE 802 protocols. Supporting IEEE 802.1as over 5G links requires precise timing packet delivery. The 802.1q enhancements, particularly time-aware scheduling, 802.1qbv, you can look these protocols up. I won't get into them. A lot of you are familiar with them. So again, the 802.1q enhancements, particularly the time-aware scheduling, which is the 802.1qbv, require the 5G system to support scheduled traffic with very low jitter. This might involve reserving specific 5G radio resources for Ethernet traffic. The coexistence of hard, real-time, and lower priority traffic requires sophisticated quality of service mechanisms in the 5G system, potentially including features like preemption of lower priority traffic. The system must also support the configuration of these features, which might involve integrating with industrial network configuration tools. To support time-sensitive networking (TSN) features, like those defined in IEEE 802.1q, big Q, 5G systems employ several advanced techniques. One key feature is the use of time-aware scheduling in the radio access network, in the RAN, where transmission opportunities are aligned with the TSN schedule. This involves precise coordination between the 5G system clock and the TSN domain clock, often achieved through techniques like Generalized Precision Time Protocol, GPTP. The 5G system also supports frame preemption mechanisms similar to those defined in IEEE 802.1 BQ BU, B as in bulk, U as in umbrella. This allows high-priority, time-sensitive frames to interrupt the transmission of low-priority frames, ensuring that critical traffic meets its timing requirements. The system employs sophisticated scheduling algorithms that can handle mixed traffic with different priority levels and timing requirements. So integration with industrial Ethernet systems often requires the 5G system to appear as a transparent bridge from the perspective of the TSN network, time-sensitive network. This involves techniques like TSN stream adaptation, where the 5G system maps TSN streams to appropriate 5G QoS flows, and TSN configuration adaptation, where TSN configuration parameters are translated into 5G system parameters. Okay, next is direct device connection. Direct device connection, also known as side link in 3GPP terminology, allows UEs to communicate without going through the network infrastructure. This can significantly reduce latency for local communications. Supporting different spectrum for direct communication than for network communication allows for more flexible use of radio resources. The clock synchronization requirements for direct connection are particularly challenging, as the devices need to maintain accurate timing without constant reference to the network. The service continuity requirements when moving between non-public and public networks involves complex handover procedures that need to be executed without disrupting time-critical applications. 5G side link communication supports various modes of operation, including network scheduled, network assisted, and autonomous modes. In network scheduled mode, the base station allocates resources for side link communication, providing tight control over interference and resource usage. In autonomous mode, devices can communicate even when out of network coverage using distributed scheduling algorithms. To support precise synchronization in direct device connections, 5G employs techniques like distributed synchronization, where devices can act as synchronization sources for nearby devices. This might involve hierarchical synchronization structures similar to those used in IEEE 1588 protocol. We just talked about this. Adapted, the IEEE 1588 v2 is one you want to look at. Adapted for the dynamic nature of device-to-device networks. Service continuity between non-public and public networks is achieved through advanced mobility management techniques. This might involve dual connectivity solutions where a device maintains connections to both networks simultaneously during the transition. The system also employs context transfer mechanisms to ensure that critical parameters, including synchronization information, are maintained during the handover process. Now, indirect network connection, where one UE relays traffic for another, presents unique challenges. The system needs to manage the additional hop in the communication path, which adds latency and potential points of failure. Supporting multicast in this scenario requires efficient routing protocols. The clock sync requirements are even more challenging than indirect connection, as the timing information needs to be relayed accurately. The 5G system needs to manage the resource allocation for both the relaying UE and the end UE, ensuring that the relay doesn't become a bottleneck. 5G relay technology supports various types of delays, including layer 2 and layer 3 relays. Sorry, not delays, relays. Layer 2 relays operate at the radio link control of the RLC or MAC layer, providing lower latency but less flexibility. Layer 3 relays operate at the network layer, offering more flexibility in routing and resource management. To minimize the impact of the additional hop in relayed connections, 5G employs techniques like cross-link interference management and dynamic relay selection. Cross-link interference management involves coordinating transmissions on the access and backhaul links to minimize interference. Dynamic relay selection algorithms choose the best relay based on factors like link quality, load, and end-to-end latency requirements. Supporting multicast in relayed scenarios involves techniques like multicast forwarding at the relay nodes and efficient multicast group management. The system also employs advanced scheduling algorithms that can efficiently allocate resources for multicast traffic across both the access and backhaul links. Let's take a look at some of the vertical industries examples. So here we want to take a look at the factories of the future. Again, the future is here. At the time of this presentation, 5G has been around, and people like myself are already working on 6G, but there is a foundation in 5G that developers of 6G needs to be very clear and use that as a foundation. So it's an improvement of 5G to 6G. So hopefully this presentation also serves a purpose, even when 5G is already being implemented in many cases. Here, let's take a look at factories of the future. That's what is indicated on the spec. In factory automation, motion control applications can require cycle times as low as 500 microseconds with jitter less than 1 microsecond. I want you to cross-check these references on the spec itself in case I made a mistake, but it's all stated on the spec. Mobile robots need both high-speed data for video and low-latency control channels. Control-to-control communication often requires deterministic latency over relatively long distances within a factory. Process automation applications, while generally having less strict timing requirements, often need to support a very large number of devices. Human-machine interfaces like augmented reality require high bandwidth for video, combined with low latency for interaction. Remote maintenance applications need to support secure remote access, often from outside the factory network. To support such demanding requirements, 5G employs a combination of radio and network technologies. For ultra-low latency applications, the system uses techniques like round-free uplink transmission and mini-slots, where it allows for very short transmission times. Deterministic latency is achieved through careful scheduling, and resource reservation, often involving techniques like semi-persistent scheduling. That's one of the techniques. For mobile robots and other moving machinery, 5G employs advanced beam management and handover techniques to maintain connectivity. This might involve predictive handover algorithms that anticipate when a device will move between cells based on its trajectory and velocity. These days, this prediction is done by AI/ML, which can be quite accurate. Supporting a large number of devices for process automation applications involves massive MIMO technology and efficient scheduling algorithms. The system also employs advanced IoT features like narrowband IoT and LTE-M, which are designed for low power, wide area coverage. For augmented reality applications, 5G uses high bandwidth capabilities combined with edge computing to minimize latency. This might involve techniques like network slicing to provide dedicated resources for AR traffic, augmented reality traffic, and application-aware scheduling to prioritize critical AR data. Here is an example of a motion control system. A motion control system is tasked with precisely controlling the movement and rotation of machine parts, such as those found in printing machines, machine tools, or packaging equipment. This simple diagram shown on here provides us a schematic representation of such a system. In this setup, a motion controller periodically sends desired set points to one or more actuators, for example, linear actuators or drives, which then execute the corresponding actions on various processes, typically involving the movement or rotation of specific components. Simultaneously, sensors measure the current state of these processes, such as the position or rotation of components, and relay this data back to the motion controller. This exchange occurs in a strictly cyclical or cyclic and deterministic manner. Cyclic would be the right word that I wanted to say. The motion controller updates the set points for all actuators, and the sensors transmit the actual values back to the controller within each application cycle. Modern motion control systems predominantly utilize industrial Ethernet technologies to facilitate these operations. Here's another picture taken out from the spec. It's titled Wire-to-Wireless Link Replacement. As the title indicated, is self-explanatory. In a traditional factory, the production environment is typically fixed, with cooperating machines interconnected via cables, wired via cables, often employing industrial Ethernet technologies like Profinet, which is the protocol which we mentioned earlier. Profinet or Profinet, don't know how to pronounce it, is an acronym. To enhance flexibility in the production setup, these wired connections are being replaced with wireless links. Consider a scenario where 2 or more machines, typically 4 or 5, collaborate during production. To replace the cables, each machine is outfitted with a UE device, user equipment device, which connects to the controller. As you can see here, the communication between cooperating machines can be categorized into 2 types: periodic traffic and aperiodic traffic. Both types are scheduled, ensuring that aperiodic traffic also adheres to the transfer intervals. The traffic requirements are viewed from the perspective of the UE, representing the maximum aggregate traffic of all links. This means that while the traffic per link may vary depending on the number of cooperating machines, the total traffic at the UE must not exceed the specified limits. Okay, enough about that. Let's take a look at another picture here, which is an example again in a small smart factory. You can see this as robots cooperating to carry something, carry an equipment or something. So in a smart factory, large or heavy work pieces, like this one big work piece, are transported by multiple mobile robots, or sometimes they're called automated guided vehicles, AGVs vehicles. These robots must collaborate closely to ensure the safe handling of these substantial loads. Like this is a tremendously heavy piece of something, heavy piece of equipment. This synchronization is achieved through a CyberPhysical control application that meticulously coordinates the drives and movements of the mobile robots and AGVs, enabling them to transport large or heavy work pieces smoothly and safely from one location to another. So this is one use of a controlled application that needs to coordinate all the entities that are taking part in the motion. The communication among these cooperating robots and AGVs necessitates exceptionally high service availability and ultra-low latency. Control commands and feedback are exchanged through periodic, deterministic communication, utilizing time-sensitive networking to maintain precision. There are two distinct variants for cooperative carrying, like this particular use case. One, transporting rigid or fragile work pieces which require extremely precise coordination among the mobile robots. Two, transporting more flexible or elastic work pieces which allow for some tolerance in coordinated movements. This higher tolerance permits either faster movement of the workpiece or longer transfer intervals, presenting a trade-off between the speed of the robots and the transfer interval. So there's a bit of a challenging or interesting point about this use case. Let's take a look at an edge computing use case, an example, one of the examples. Digital twin-based production quality maintenance. You can see here, this is an example of how you would manage production in a factory using the digital twinning technology. A digital twin is a virtual representation of a product or production system used to simulate, predict, and optimize their performance. In the future, and the future is now, digital twin production control systems enhanced with augmented reality will be widely utilized in a lot of factories, if not all of the factories. In this scenario, that can afford it. In this scenario, a digital twin integrates physical data with a virtual model to simulate real-time operations of a system. A digital twin production control systems can be automated using machine data combined with AI/ML algorithms. The AI/ML trained data, once processed, can generate control commands that are executed by a control function running on the edge cloud. Additionally, telemetry data can be used as input, with the digital twin model's output fed to an AR server, delivering low-latency AR streams to manual operators in the factory. Simultaneously, this output can serve as input for further AI/ML processing. A process control function can compare machine data, for example, position, rotation level, speed, sensor data, high-speed photography, And high-resolution video from the manufacturing line, issuing commands for corrective measures if necessary. These process control functions reside on the edge infrastructure, with corrective inputs sent back to the production system control function. In fact, this is not exactly factory scenarios for the future, but this is, as I said earlier, happening in a lot of factories today already. Corrective actions or commands for misalignments derived from the processed output can be sent in two ways. One, manual process with an augmented reality server, or automatic process with an AI/ML process. General high-level service requirements for edge computing in digital twin-based production inspection, by and large, are the following. So here are the general requirements. High bandwidth wireless data, which is essential for both uplink and downlink, dependent on video encoding, frame rate, and resolution requirements. Second, timing accuracy and low latency, about less than or equal to 20 milliseconds. High availability, ensuring constant communication network uptime. Security, including data encryption, connection authentication, and user authorization. Quality of service, ensuring consistent performance across various UE to application connection sessions, video streaming, sensor data, control data, etc. UE mobility and session continuity. This one is optional but beneficial to have. So this is one of the use cases of digital twinning that we just looked at. Periodic telemetry data. This is one last thing I want to mention. Periodic telemetry data and video images from the digital twin in the production system are analyzed, and the processed outcome is sent back to the system for adjustments to machine components. So again, to sum it all up, the diagram on this slide illustrates a digital twin use case steps for managing production in a factory, covering both manual and automated operations. What is this going to bring us? One big thing is low latency AR overlays. Integration of AI/ML techniques is of big benefits a great deal. What it does is it identifies manufacturing issues, improve product quality, and enable offline adjustments for optimization, adaptations, and preventive maintenance. This is a pretty elegant and efficient approach to digital twin-based production, quality maintenance, which leverages this power of edge computing, augmented reality, and AI/ML to enhance factory operations and ensure high-quality production outcomes. Now let's move on to electric power distribution, which is another vertical domains that we want to take a look at. Primary frequency control requires very fast response times, typically within 30 seconds of a frequency deviation. This requires the 5G system to support wide area, low latency communication. Distributed voltage control involves coordinating many devices across a wide area to maintain voltage levels. Distributed energy automation applications like fault location, isolation, and service restoration. There is an acronym for it. FLISR is an acronym which stands for fault location, isolation, and service restoration, require the system to quickly disseminate information about grid status and control commands. Smart grid applications often use protocols like IEC 61850, which the 5G system needs to support efficiently. Advanced meter infrastructure, AMI, acronym for that. We have so many acronyms. That requires the system to handle a very large number of devices, each sending relatively small amounts of data. To support these applications, 5G employs several key technologies. For primary frequency control, the system uses ultra-reliable low latency communication features to ensure rapid, reliable delivery of control messages. This might involve techniques like diversity transmission, where critical messages are sent over multiple paths to increase reliability. For distributed voltage control and energy automation, 5G supports wide area IoT technologies like narrowband IoT and LTE-M, stands for machine, which provide extensive coverage and good building penetration. The system also employs advanced multicast broadcast techniques to efficiently disseminate grid status information to many devices simultaneously. Supporting protocols like IEC 61850 involves careful mapping of protocol messages to appropriate 5G quality of service classes. The system also supports time synchronization features that align with the timing requirements of these protocols, often involving integration with PTP systems. Again, PTP stands for Precision Time Protocol Systems. For advanced metering infrastructure, 5G employs massive IoT technologies that can support a very large number of low-power devices. This includes features like extended discontinuous reception, EDRX, and power saving mode, PSM, to maximize battery life in metering devices. All right, this is another picture here that's taken out from the specification depicting distributed automated switching for isolation and service restoration. A fault in the power distribution grid can be a highly stressful event. Fortunately, there are self-healing solutions designed for automated switching, fault isolation, and service restoration. Remember what the acronym is that I just told you? Anyways, these solutions are particularly well suited for managing outages that affect critical power consumers such as industrial plants or data centers. For these critical consumers, supply interruptions must be resolved in less than a second. And automated solutions are capable of restoring power within just a few hundred milliseconds. Here on the slide is an illustration of a distribution ring and a fault. You could see that is depicted by a flash of lightning icon. That's a fault. The fault location, isolation, and service restoration, the acronym I just told you, FLISR solution, comprises switch controller devices specifically designed for feeder automation applications. These devices support the self-healing of power distribution grids with overhead lines and act as control units for reclosers and disconnectors. The system employs fully distributed, independent automated devices with the logic residing in each individual feeder automation controller located at the poles in the feeder level. Each feeder section is equipped with a controller device. Through peer-to-peer communication among these controllers, the system operates autonomously without requiring a regional controller or control center. However, all self-healing actions are immediately reported to the control center to maintain an up-to-date grid status. Typically, the controllers isolate faults and conduct self-healing of the distribution line within 500 milliseconds. You can correct me if these numbers are not entirely accurate, but I think they are. Peer-to-peer communication is facilitated via IEC 61850, so-called GOOS messages. GOOS is an acronym for Generic Object-Oriented Substation Event, GOOS, messages, which provide data transmission as rapidly as possible using layer 2 multicast messages. These messages are sent periodically during steady-state operations, with intervals changing in fault situations. Each controller sends these messages to several or all other controllers on the same feeder, and they are not acknowledged. While the service bit rate per controller is low during steady-state operations, GOOS bursts, those messages bursts, GOOS messages in specific, with a high service bit rate occur, especially during fault situations. Multiple or all controller units of the feeder send GOOS messages nearly simultaneously during the fault location, isolation, and service restoration procedure, ensuring low end-to-end latency. Pardon me. Here's another diagram here. It's very small. I don't know if you can see all the text on the picture. This is about the intelligent distributed feeder automation system supported by 5G connections. And it is designed to perform intelligent judgment analysis, fault location, and power supply restoration for non-fault areas. As the diagram shows, this system comprises a distribution master station, distribution terminals, switch stations, and the communication system, which is including UEs in substations, the 5G network itself, and the data network. The distribution master station is primarily used for information gathering and human-computer interaction. The distributed terminals collect feeder status information and are responsible for fault judgment, location, isolation, and power supply restoration based on this information. Actions taken by the distributed terminals are reported back to the distribution master station. The 5G communication system facilitates communication among these distributed terminals, while the distribution master station is typically connected to the 5G system via a data network, which falls outside of the 3GPP scope. The distribution master station manages multiple distributed terminals, each equipped with a 5G UE, to exchange collected data with other terminals. From an application perspective, the communication between distributed terminals is peer-to-peer. The 5G communication service must exhibit very high availability, hence at least 2 communication links are typically deployed for hot standby or synchronous data transmission between terminals. All right, here's another example. Distributed energy storage. Distributed power generation encompasses various sources like solar, wind, fuel cells, and gas. These sources typically have low power density and are deployed in a decentralized manner. This decentralization presents technical challenges for smart grid operators. When integrated into the electrical grid, distributed power generation complicates energy flow. As users often function as both consumers and producers of electricity, they are known as prosumers. With a play of words, prosumers. Consequently, the direction of current within the grid can vary at different locations and times of the day. The information exchange in a distributed energy grid involves not only power generation data, but also control commands for distributed energy storage equipment. For example, commands might include instructions to change load characteristics to achieve a flexible electricity grid. As depicted on this picture, a distributed energy storage grid requires information exchange between the Distributed Energy Storage Management Platform, again there's an acronym for it, DESMP, and Distributed Energy Devices, DEDs. Each DED, and Distributed Energy Device, is a plug-and-play device that periodically collects and reports its energy information such as battery energy levels, charge and discharge status, and energy alarms. This information is transmitted via 5G UE to the DESMP. Again, DESMP stands for Distributed Energy Storage Management Platform. So the DESMP is responsible for regularly managing the DEDs. This includes monitoring their operational status, controlling their working modes, and configuring their energy parameters. We're going to look at another vertical domain, central power generation. Wind power plant networks need to coordinate many individual turbines, often spread over a large area. Here, I think 7 nines. No, 8 nines, I think. 99.999999. 8 nines% availability requirement translates to only 0.31 seconds of allowable downtime per year. The 60 millisecond maximum latency requirement is needed for fast control loops that adjust turbine parameters based on current wind conditions. These networks often need to operate in harsh environments, especially offshore, which places additional requirements on the reliability of the communication equipment. The system also needs to support the high bandwidth requirements for transmitting large amounts of sensor and monitoring data from each turbine. To meet these extremely high availability requirements, 5G employs multiple reliability enhancing techniques. This includes multi-connectivity solutions, where each turbine maintains connections to multiple base stations simultaneously. The system also uses advanced error correction coding and hybrid automatic repeat request (HARQ) mechanisms to minimize packet loss. The low latency requirements are met through a combination of radio and network optimizations. This might involve techniques like edge computing, where control functions are moved closer to the turbines to minimize network delays. The system also employs advanced scheduling algorithms that can prioritize critical control traffic over less time-sensitive monitoring data. For operation in harsh environments, 5G equipment designed for these applications often includes ruggedized hardware with enhanced protection against environmental factors like extreme temperatures, humidity, and salt spray, since they might be installed in the ocean. The system also employs advanced link adaptation techniques that can maintain connectivity even in challenging radio conditions such as during storms. To support the high bandwidth requirements for sensor and monitoring data, 5G uses its enhanced mobile broadband capabilities. This might involve techniques like carrier aggregation to provide high data rates and QoS, quality of service mechanisms, to ensure that high volume monitoring traffic doesn't interfere with critical control traffic. Okay, here's an example of smart distribution transformer terminal. Here's a workflow for it. Okay, a smart distribution transformer terminal is typically deployed within a distribution transformer area and is capable of supporting multiple energy applications simultaneously. The terminal collects various types of energy data and transmits them to an energy application platform. Here's an example workflow for a smart distribution transformer terminal. Generally, the connections between the Smart Distribution Transformer Terminal and the Energy Application Platform are facilitated by the 5G system. Additionally, the connections between energy end devices and the Smart Distribution Transformer Terminal may also be provided by the 5G system. In this scenario, approximately 300 to 500 energy and devices are connected to a single Smart Distribution Transformer Terminal. Each application requires an average uplink surface bit rate of more than 2 megabits per second between the Smart Distribution Transformer Terminal and an energy end device. The communication distance ranges from 100 meters to 500 meters. On this specification, you can see provided KPIs, key performance indicators, for all the use cases that I cited here. So for details, go back to the spec and obtain those specific actual KPIs. Another example here is about connected hospitals. Robotic aided surgery requires extremely low latency, less than 2 milliseconds, and high availability, 8 nines, 99.999999%, when the surgeon and robot are co-located. This is to ensure that the surgeon's actions are translated to robot movements with no perceptible delay. We're dealing with human life, so this is extremely important. For remote surgery, while the latency requirement is slightly relaxed, less than 20 milliseconds, it needs to be maintained over potentially long distances. The system needs to support high-quality video streams, potentially multiple streams, for different camera angles, simultaneously with a low-latency control channel. For diagnostic applications, while the latency requirements are less strict, the system needs to support the transfer of large medical imaging files with perfect integrity. To achieve the ultra-low latency required for co-located robotic surgery, 5G employs several advanced techniques. This includes the use of mini slots and grunt-free uplink transmission. Again, these techniques were used in a lot of these applications, which we already talked about. So these two techniques are used to minimize scheduling delays. The system also uses edge computing techniques to process control data as close to the robot as possible, minimizing network traversal time. For remote surgery applications, 5G uses its network slicing capabilities to provide dedicated end-to-end resources for the surgical data. This might involve creating a slice with guaranteed QoS, quality of service, that spans multiple network operators if the surgery is conducted over long distances. The system also employs advanced congestion control mechanisms to maintain consistent performance even under varying network conditions. Supporting multiple high-quality video streams involves the use of 5G's enhanced mobile broadband capabilities. This might include techniques like multi-connectivity, where video data is sent over multiple paths to increase reliability and throughput. The system also supports advanced video coding standards to efficiently transmit high-resolution, high frame rate video. For diagnostic applications involving large file transfers, 5G employs robust error correction and checksumming mechanisms to ensure data integrity. This might involve techniques like automated repeat request, ARQ, at multiple protocol layers to detect and correct any transmission errors. So to further illustrate, robotic-aided surgery, here's a simple diagram. Robotic-aided surgery excels in performing invasive surgical procedures that demand delicate tissue manipulation, and access to hard-to-reach places or areas. This is accomplished through sophisticated systems that translate the surgeon's hand movements into smaller, precise motions of tiny instruments which can bend and rotate far more intricately than a human hand within the patient's body. These systems also filter out hand tremors, enabling more consistent outcomes for existing procedures and facilitating the development of new procedures that unaided manipulation cannot achieve due to accuracy limitations. In a typical robotic setup for telesurgery, the robot and the surgeon's console can be co-located in the same operating room, communicating through a non-public network, NPN. Alternately, when specialists and patients are separated by vast distances, that is to say hundreds of kilometers, they can exchange data via communication services provided by PLMNs, public land mobile networks. This medical application can be instantiated either on site or in the cloud, with the role of generating appropriate haptic feedback based on instrument location, velocity, effort measurements, and images from surgical instruments, and a 3D preoperative patient body model. This provides tactile guidance by constraining where instruments, such as a scalpel, can go. It's helping to filter motion control commands to enhance closed-loop stability. Typical robotic surgery systems feature around 40 actuators and an equal number of sensors, enabling the computation of data rates required for executing specific movements. Human tactile sensitivity is remarkably high, with tactile sensing bandwidths of about 400 Hz, referring to the frequency at which stimuli can be perceived. Consequently, haptic feedback systems generally operate at frequencies around 1000 Hz. This rate applies to the update of all information used in generating haptic feedback, such as instrument velocity and position. The robot control process involves the surgeon's console periodically sending set points to actuators. Actuators executing the given processes. Sensors, and the last point is sensors sampling velocity, forces, positions, etc., simultaneously and returning that information to the surgeon's console at a rate of about 1 kHz. Unlike machine-to-machine communication, robotic-aided surgery places a human in the middle of the control loop. This means the console generates new commands based on system state collected in the previous 1 kHz cycle and the surgeon's hands movements. Each piece of equipment in a robotic telesurgery setup, for example with endoscopes, image processing systems, displays, motion controllers, and haptic feedback systems, they all need to be synchronized using a common clock, either external or provided by the 5G system. Synchronization is often achieved through dedicated protocols such as PTP version 2, which we talked about a number of times earlier, ensuring the consistency of haptic feedback and displayed images at the master console, and enabling the recording and offline replay of the entire procedure. Next let's take a quick look at the robotic-aided diagnostics or diagnosis. Here, the robotic-aided diagnosis enables a remote expert in the central hospital to control a diagnostic robotic system deployed in a local medical facility. Examples of such systems include haptic feedback tools used for palpation, deployed in facilities such as mobile specialist practice units, or ultrasound probes deployed in ambulances or medical facilities. In a typical telediagnosis setup, specialists and patients are separated by considerable distances, typically dozens of kilometers, and exchange data via communication services provided by PLMNs, which is short for Public Land Mobile Networks. The medical application can be instantiated on either side or in the cloud, with its primary roles being generating appropriate haptic feedback based on instrument location, velocity, effort measurements, and images from diagnostic instruments. We went through this earlier. It also helps to filter motion-controlled commands to enhance closed-loop stability. Communication service errors. Corruption errors can occur due to interference or hardware issues. The 5G system needs robust error detection and correction mechanisms to mitigate these. Unintended repetition and incorrect sequence of errors can be particularly problematic for control applications, requiring the system to implement sequence numbering and potentially discard out-of-sequence packets. Loss of messages is handled differently depending on the application. Some may require guaranteed delivery with retransmission, while others may prefer to skip lost messages to maintain timeliness. Masquerade and insertion errors are particularly concerning from a security perspective, requiring the system to implement strong authentication and integrity protection mechanisms. To address corruption errors, 5G employs advanced forward error correction (FEC) coding schemes, including polar codes for control channels and low-density parity check (LDPC) codes for data channels. These are complemented by cyclic redundancy check (CRC) codes for error detection. The system also uses hybrid automatic repeat request (HARQ) mechanisms that combine FEC with the retransmission to efficiently handle errors. For sequence-related errors, 5G implements robust packet sequencing mechanisms at multiple protocol layers. This includes sequence numbers in the RLC Radio Link Control Protocol and the Packet Data Convergence Protocol, PDCP. The system also supports in-sequence delivery options that can reorder packets before delivery out to the application. Message loss is handled through a combination of linked layer and end-to-end mechanisms. At the linked layer, 5G uses HARQ with soft combining to efficiently recover from transmission errors. At higher layers, the system supports both acknowledged and unacknowledged transmission modes, allowing application to choose between reliability and timeliness. To prevent masquerade and insertion errors, 5G implements strong security measures. This includes mutual authentication between devices and the network, integrity protection for control plane messages, and optional encryption for user plane data. The system also supports advanced security features like network slicing, isolation, to prevent unauthorized access to critical resources. The logical link concept provides an abstraction of the end-to-end communication path, independent of the underlying network topology. This allows for consistent specification of requirements across different network implementations. Message transformation includes processes like fragmentation and reassembly, which the 5G system needs to perform efficiently to meet latency requirements. The communication devices UE, space stations, core network elements, etc. They need to be designed to meet the stringent performance requirements while also being robust enough for industrial environments. The overall communication system needs to manage resources efficiently to support multiple services with different requirements simultaneously. In 5G, the logical link concept is implemented through the use of QoS flows and PDU sessions. QoS flows, quality of service flows, provide a granular way to specify service requirements, while PDU sessions represent the overall connectivity context. The system supports multiple PDU sessions per UE, allowing for logical separation of different services. Message transformation in 5G involves several protocol layers. At the PDCP layer, the system performs header compression to reduce overhead. The radio link layer, RLC layer, handles segmentation and concentration of packets to fit them into the available transport blocks. The MEG layer performs multiplexing and prioritization of logical channels. 5G devices for industrial environments often include features like enhanced thermal management to operate in extreme temperatures, ruggedized enclosures for dust and water resistance, and advanced power management for extended operation. Base stations might include integrated edge computing capabilities to support low latency applications. Resource management in 5G involves sophisticated scheduling algorithms that can handle mixed traffic with different QoS requirements. This includes techniques like semi-persistent scheduling for periodic traffic, punctuated scheduling for urgent transmissions, and dynamic sharing of resources between different network slices. Here's another picture from the spec for our discussion on communication in automation. We adopt a definition of the area of consideration for industrial radio communications. On this picture, the blue objects represent the communication system. Other objects represent an automation application system. So in this context, a distributed automation application system is depicted. The system comprises a distributed automation application, which aggregates various automation functions, including those in sensors, measuring devices, drives, switches, I/O devices, and encoders. All these functions contribute to the control of physical objects. The distributed functions can be interconnected using field bus systems, industrial Ethernet systems, or wireless communication systems. The primary role of these communication systems is to ensure the distribution of messages among the distributed automation functions. For cyber-physical control applications, the dependability of the entire communication system and its components or links is crucial. Communication functions are implemented through corresponding hardware and software. For the automation application system to operate effectively, messages must be exchanged between spatially distributed application functions. This exchange occurs at an interface known as the reference interface, which lies between the automation application system and the communication system. Required and guaranteed values for characteristic parameters that describe the behavioral properties of the radio communication system, as well as some influence quantities, pertain to this interface. The behavior of wireless communication is influenced by the communication requirements of the application, for example, end-to-end latency. The characteristics of the communication system, for example, transmitter output power, and the transmission conditions of the medium, for example, signal fluctuations caused by multipath propagation. From the application point of view, general requirements for the time and failure behavior of a communication system are mostly related to an end-to-end link. It is assumed in this document that the behavior of the link is representative of the communication system as a whole and the entire scope of the application. This picture is talking about a little bit more about the logical link concept. Building on the general approach outlined on this spec, the logical link can be considered a crucial component within the area of consideration. The conditions under which its functions are performed are essential for the dependability of the automation application system. So a logical link connects a logical endpoint in a source device to a logical endpoint in a target device. These logical endpoints form part of the reference interface and may group multiple logical endpoints together. The primary function of the logical link is to transmit a sequence of messages from the logical source endpoint to the correct logical target endpoint. This is achieved by transforming each message into a form that ensures error-free transmission. The transmission process may involve various procedures such as repetitions to fulfill this function. Once the message is transmitted, the transported package or packages is converted back into its original message form. The message must be available and accurate at the target within a defined time frame. And the sequence of messages at the target must mirror the sequence at the source. What is an asset logical link? So regarding the previous slide and the functional units and influences, let's take a look at the functional units here, if you can see the different text clearly on this picture. The functional units necessary to fulfill this communication function are depicted on this diagram, which is taken straight out from the specification, the 3GPP specification. The performance of the required function can be impaired by various influences, potentially leading to communication errors. The occurrence of such errors affects the values of the relevant dependability parameters of the logical link. So as you can see on this diagram, the logical link is illustrated as an asset, highlighting the essential components and their interactions. The diagram underscores how these components work together to achieve reliable communication despite the potential for errors. Understanding these influences and their impacts on the logical link's dependability is critical for maintaining the integrity and performance of the automation application system. Timeliness and accuracy concepts. The timeliness concept defines an acceptable window for message delivery. For some applications, this window might be as small as a few microseconds. Deviation is a key metric for assessing the performance of time-sensitive networking features. Earliness can be as problematic as lateness for some applications, particularly those that rely on precise timing of actions. The 5G system needs to minimize both earliness and lateness to support these applications. These concepts are particularly important for implementing features like time-sensitive networking, TSN, over 5G, where precise timing of packet delivery is crucial. In 5G, timeliness is supported through a combination of radio and network features. At the radio level, this includes the use of flexible numerology and mini slots to allow for precise timing of transmissions. At the network level, it involves careful scheduling and prioritization of traffic to meet timing requirements. Deviation in 5G is minimized through techniques like precise timing advanced adjustments to account for propagation delays and jitter buffers in the receiving devices to smooth out timing variations. The system also employs advanced clock synchronization mechanisms to maintain coexistent timing across the network. To handle earliness and lateness, 5G supports features like scheduled traffic where transmissions are aligned with specific time windows. This is particularly important for supporting TSN features. The system also provides mechanisms for applications to specify their timing requirements, allowing the network to optimize its behavior accordingly. For TSN support, 5G acts as a bridge between TSN domains. This involves translating TSN timing requirements into appropriate 5G QoS parameters and providing mechanisms to synchronize the 5G system clock with the TSN domain clock. The system also supports features like hold and forward, where packets are held until their scheduled transmission time to maintain precise timing. 5G systems implement sophisticated packet scheduling algorithms that handle mixed traffic with different timeliness requirements. This might involve techniques like earliest deadline first, EDF, scheduling, adapted for the wireless environment, or multi-level priority queuing with preemption for critical traffic. "5G in industrial automation." The global time domain typically uses a reference like GPS time or the IEEE 1588 Grandmaster Clock time. Working clock domains might be synchronized to a local reference, such as a specific machine's clock. The 5G system needs to transport timing information for both types of domains. Merging of working clock domains is a complex process that might involve adjusting the timing of one domain to match another, which the 5G system needs to support without disrupting ongoing operations. The 5G system might provide timing support through features like synchronized frame transmission or by transporting external time protocols like IEEE 1588 version 2 with minimal and consistent delay. To support multiple time domains, 5G employs techniques like time domain isolation, where different network slices can operate with independent time bases. This allows the system to support both global time sync and local working clock domains simultaneously. For precise timing transport, 5G uses features like synchronized Ethernet, I mentioned this earlier, SYNC-E, in the backhaul network, and IEEE 1588 support in the radio access network, in the RAN. Base stations can act as transparent clocks or boundary clocks in the IEEE 1588 hierarchy, allowing for accurate propagation of timing information. So merging of working clock domains is supported through features like adaptive time synchronization, where the system can dynamically adjust its timing parameters to align with changing network configurations. This might involve techniques like gradual frequency adjustment to smoothly transition between different time bases. Here's another diagram that elucidates the terminology related to communication interfaces pertinent to vertical applications. Given that the 3GPP network does not encompass the complete ISO-OSI communication stack. It is crucial to differentiate between two things: the perspective of vertical applications and the perspective of the 3GPP network. This diagram here presents a simplified version of the communication stack. Within the stack, the PHY layer, the MAC layer, and portions of the IP layer are components of the 3GPP network, collectively referred to as the lower communication layers, LCL. The communication stack also integrates an application layer with the OSI layers responsible for delivering data to the application, known as the higher communication layers, HCL. The interface between the LCL and HCL is termed the Communication Service Interface, CSIF. Remember, we talked about this earlier. So this is sort of a revision of what we already talked about earlier in a stack format, so you can see at a glance what the stack looks like for communication services. When evaluating overall system performance, it is vital to distinguish between the performance of the 3GPP network, encompassing only the LCL and measured at the CSIF, and the overall system performance, which includes the application layer comprising both the LCL and the HCL. The orange arrow represents the vertical applications perspective, while the blue arrows illustrate two methods of measuring the 3GPP network's performance, either including or excluding the IP layer. You can see the transmission of messages from a source application device, for example, a PLC, programmable logic controller, to a target application device, for example, an industrial robot. Oh, I might have jumped a couple of slides. Let's take a look at this one. Yes, this is the second to the last slide. Reliability in 3GPP terms is often measured as a packet error rate or success rate within a specific time window. For example, a reliability of 5 nines might mean successfully delivering 5 nines, 99.999% of packets within a 1 millisecond window. Communication service availability, on the other hand, is measured over much longer periods and takes into account factors beyond just packet delivery. For example, if packets are delivered reliably but with too much latency, the service might be considered unavailable. The relationship between these metrics is complex and depends on factors like the survival time of the application. Understanding this relationship is crucial for translating application requirements into network performance requirements. So, to achieve high reliability, 5G employs techniques like multi-connectivity, where data is sent over multiple paths to increase the likelihood of successful reception. We talked about this multiple times. The system also uses robust coding schemes and hybrid HARQ mechanisms to minimize packet loss. Communication service availability is enhanced through features like network redundancy and rapid failure detection and recovery mechanisms. This might involve techniques like dual connectivity, where a device maintains connections to multiple base stations simultaneously, allowing for seamless failover in case of issues with one connection. The relationship between reliability and availability is managed through sophisticated QoS mechanisms, quality of service mechanisms. This includes features like QoS flow control and adaptive modulation and coding, which allow the system to dynamically adjust its behavior to maintain the required level of service. For applications with specific survival time requirements, 5G supports features like semi-persistent scheduling and grant-free transmission, which can ensure that critical data is transmitted even in challenging network conditions. Conclusion, finally, and even for the last slide, it was sort of a summary of this spec. In conclusion, this specification sets the stage for 5G systems to support a wide range of industrial applications. It requires 5G systems to provide capabilities far beyond traditional mobile broadband, including ultra-reliable low-latency communication, time-sensitive networking, high-precision positioning, and support for both very high bandwidth and massive number of devices. Meeting these requirements will involve advances in radio technology like flexible numerology and mini-slots in 5G NR, network architecture like edge computing for low latency, and core network functions like an advanced QoS management. As these capabilities are implemented or have already implemented, 5G has the potential to become the unified networking technology for industrial applications, replacing a variety of specialized wired and wireless technologies currently in use. The implementation of these requirements involves a complex interplay of various 5G technologies. For example, network slicing allows the creation of virtual networks tailored to specific industrial applications, each with its own performance characteristics. Edge computing brings processing power closer to the devices, enabling ultra-low latency applications. Advanced antenna technologies like massive MIMO and beamforming improve coverage and capacity, particularly important for dense industrial environments. The integration of 5G with existing industrial systems presents both challenges and opportunities. It requires careful consideration of factors like legacy system support, migration strategies, and security implications. However, it also opens up possibility for new types of industrial applications that were previously not feasible with existing communication technologies. As 5G continues to evolve and the advent of 6G, future releases are expected to further enhance these capabilities, potentially including features like integrated sensing and communication, improved support for time-sensitive networking, and even tighter integration with industrial control systems. This ongoing development ensures that 5G will continue to meet the evolving needs of industrial applications well into the future. Thank you for your attention to this presentation. Hope it is somewhat helpful. Thank you.